Okay, should we start? All right, so I'm going to continue the discussion of pyrochlore magnetism. So in this particular material, so I'm just going to focus on one material. So in this family of materials where one of the sublattices involves iridium, you have a whole slew of new phenomena appearing, which go under the rubric of all in, all out. So this seems like the most likely candidate for this ordered magnetic state, and I'll explain in a minute about what that is. So this is the work of Ken Liang. We were working with Timothy Xue and Liang Fu, who came with this very interesting idea that's motivated this experiment with samples from Nakatsuji's group in Tokyo. So I'll first introduce the pyrochlore iridates and then talk about what symmetry and magnetization imply in the all-in, all-out states, and the finding of something that we call orthogonal magnetization, which involves the notion of selecting a particular chirality. And then I'll talk about some puzzles that result from this study. Okay, so there's been a push to look at topological concepts into the regime where the interactions are strong, right? Because up to now, all the systems studied experimentally have interaction plays no role. It sure would be nice to have a system where you can tune the interaction. And theorists have sort of gravitated towards the iridates as the best candidate. Unfortunately, the material is difficult to work with, difficult to grow, and samples are not very good. But anyway, this is sort of the promised land if we could go into this regime. U is the Hubbard U, right? The Hamiltonian is written here. That's the on-site repulsion. And lambda, as indicated, is the strength of the spin-orbit interaction, both normalized to the hopping integral. So in the system with where U is negligibly small, that's the playground for the last 5 to 6 years on topological materials. And when you get U up there, you're supposed to get into all these very exciting states, from wild semi-metals and topological insulators, even to the spin liquid. The pyrochlores are rather complicated. They are two sublattices, each one comprised of corner-sharing tetrahedra. So here, let's see. Anyway, this is a mess. But if you remove one of the sublattices, you find that the center of the tetrahedra has this zinc blende type structure. And so you know from zinc blende, which is the structure of diamond and gallium arsenide, right? You have two atoms that are on this diagonal and two other atoms on this diagonal. Now you decorate the atoms with the tetrahedra, and you have them corner sharing, and you get one of the sublattices. The other one is displaced by a fraction of a unit cell and also has the same symmetry. And as I emphasized, they all have this 227, and you can stick in any of the transition metal elements and now even rare earths and get a whole slew of magnetic phenomena. The iridates, the pyrochlore iridates are quite interesting. People have actually put in all kinds of rare earths, and they trigger a ordering transition at a fairly high temperature. The nature of this magnetic ordered state, I think it's still under debate. Most people think that it's what's called the all-in, all-out state. And associated with this transition is a metal insulator transition when you are on the right side of the phase diagram, right? So when you have a very large ionic radius, you go from a metal to an insulator, and the resistivity can climb by 6 orders of magnitude. But when you're on the left side, it's always insulated. So it's not strictly a metal insulator transition, it becomes more apparent for these layers. So I'm going to talk about the European element, and yeah, the transition occurs at 120 Kelvin.
So, question?
Yeah.
What kind of transition is this from when you go from the blue region to the yellow region? Meaning metal to non-metal?
You mean what happens when you go from here to here?
Yeah.
Well, there's no transition. It just has this very smooth variation. Right? Basically, you're sitting, let's say, at 200 Kelvin. There's no sign of any transition. The electronic states are not very well understood. What causes this to rise, like an insulator? Is there a gap? There's no sign of a gap. Yeah. So that's it, I think it's a fair statement. No one really understands transport in this series of materials. There is evidence that when you train the material, it can change the conductivity significantly. So here are infrared reflectivity experiments from Tokura's group showing that there's a big difference in the Drude weight between trained and untrained samples. So this is the neodymium member. A recent very interesting experiment from Ziek Shen's group by Eric Ma show that the domain walls are actually conducting. So probably the training is aligning the domain walls so that the conducting paths become long range, or the opposite. But anyway, so there's a lot of interest in these materials. There's a long paper by Imada that claims that associated with the iridates are wild nodes. Yeah, so the whole shift of attention from topological insulators to three-dimensional topological materials, wild systems, occurred around 2011 when Ashwin Vishwanath pointed out that the iridates may actually, or the advanced LDA calculations show that they actually have something like 12 pairs of wild nodes. There are these little dots here, perhaps with Fermi arcs. So, but the experiments were very difficult on the iridates, and but this caused an explosion of interest in wild physics. So this is the material that triggered it. And of course, as many of you know, tantalum arsenide eventually became the primary focus.
That training that you write there, is that similar to memory?
I don't know. I don't know what they mean by training. It's probably running the field up and down, or field cooling.
It looks like that it has some kind of memory.
Oh yeah. Oh well. I mean, magnetic systems all have memory. All magnetic systems have memory.
And it has nothing to do with spin classification.
No, it has to do with pinning of domain walls. Yeah. Right? Because even the simplest magnets, they're full of domains. And training is when you take a magnet and you keep rubbing the sample, and that aligns the domain walls, flushes them out. So, but I'm not sure in this context what you mean by training. I confess that I haven't read this paper. These are slides from my study.
What techniques were used to get the images in CD?
Sorry?
What techniques were used to get
The technique?
Yeah.
So this is called a microwave scanner. So they bring in, it's inspired by STM, but on a very broad scale. So they bring in a very sharp tip and they walk it up to the sample. and the RF impedance will shift the resonance frequency of your microwave signal. So imagine you have a resonating cavity. Of course, it's all done in a much more elegant way, but as the tip gets close to a conducting region, it will shift the frequency slightly.
It's like echolocation for the house.
Yeah, that's right. Yeah. So it's like a scanning probe of local conductivity. And when ZX came up with this idea, he walked it by me and said, "Man, there's nothing to be learned by doing that." but now it's appearing to be a very powerful tool, and they can detect regions, local regions that are more conducting than others. Okay, so we're back to the pyrochlore again. They grow with these beautiful triangular facets. And now, okay, so you remember the dysprosium titanate, right? That's the canonical archetypal spin ice. It's 2 in, 2 out, right? 2 of the spins point in and 2 point out. Now we're talking about all in or all out, right? So this is a cartoon sketch of that configuration. So this tetrahedron, all the spins point out, and the middle one, they all point in. And the time reverse partner has exactly the opposite pattern. So this is the state that we are interested in. And there's really no proof that this is the magnetic state, but it seems to be the one that all experiments are pointing to. You can okay, from LDA calculations, many groups, especially ones led by Yongbek Kim, have examined which of these states is most stable. These are the hopping integrals and the interaction, Hubbard interaction strength. And within a certain window of the hopping integral, the all-in, all-out seems to be stable. But then there are these other configurations which are consistent with the pyrochlore group, point group symmetry that may come in. And this, okay, this will play some role in our experiment as well. So the experiment that I'm going to talk to you about, this appears to, again, to be the most likely candidate, but there's no acid proof that we have seen. Here is a view which is perhaps easier than the usual lattice structure. If you look along the 1-1-1 direction, right, the body diagonal, then the tetrahedra form these planes. And so you have the hexagonal plane alternating with triangle configuration. So this is the usual picture that physicists actually like to work with. A little word about the iridate. All right, so the reason for the interest on the iridate is because iridium has a very large spin-orbit interaction. So your familiar EG and T2G splitting, let's say that you might be familiar with from cuprates, is completely scrambled, right? So the T2G states, there are 3 of them, and these are the DXY, DXZ states. Because of spin orbit, now J is the good quantum number. And it splits into 2 down here and 1 up there. So with 5d electrons in iridium, 4 plus, you have 1 hole in this manifold. And so it's a spin half system, despite the strong spin orbit interaction. So over the years, there's been some experiments. So I'll just select a few of them. First of all, there's evidence from USR that you have a time reversal breaking. So it's some kind of a magnetic state below the transition, and you pick up these oscillations of the USR. So the way the experiment's done is, you shoot muons into your system, and the muons just sit anywhere, right? So there are places in the lattice that are favored, but honestly, in the experiment, you don't really know where to sit. But if there is an internal magnetic field that appears because of long range order, the muon will start to precess, right, in the magnetic field. And it decays. So the last direction of the muon spin dictates where the photon comes out. So if you place a detector far from the sample, maybe you have two of them, you'll find that the photons come out in one direction, and then a few microseconds later they come out, they drop in intensity. So the observation of these oscillations of the photon signal are, well, experimentally stick to the signature of breaking of time reversal at the local level, right where the muon sits. The neutron scattering, so here is being plotted the intensity of the Bragg peaks versus a calculation. And it's consistent with the all-in, all-out, right? But this is based on fit rather than acid proof. People don't really have a good idea what to expect from all-in, all-out. And here, this is some resonant X-ray scattering, again, showing some data that many people take this to be more convincing than the fit here. But anyway, this, I think, are the experiments that seem to indicate all. So the experiment that I'm going to talk about was motivated by a remark by Liang Fu to me that actually if you have the ideal all-in, all-out state, the magnetization should be very strange because you don't have linear order coupling. And by applying group theory, you predict that the coupling actually is at a rank tree level, which will mean nonlinear magnetization and also a breaking of chirality. And that seemed like a very interesting idea to pursue, and so this is the story I'm going to talk about. Okay, well, why is it different, right? So let's step back a little bit. So the community refers to the all-in, all-out loosely as an antiferromagnet, right? Because in one tetrahedron, the spin local moments all point in, and the next one, they all point out. So it looks like an up-down, icing like a symmetry. But there's one crucial difference when you think about it experimentally. When you apply a field, how does the system respond, right? So let's go back to a conventional antiferromagnet. And so here's a cartoon, right? So the spins are, right, left. And in zero magnetic field, you would plot the sublattice magnetization, call it MA and B, and they would point away from each other, right? Now you apply an external magnetic field, and it's crucial which direction you apply it to. If your external magnetic field is perpendicular to the easy axis, so this is the easy axis, right? Then it's not surprising, the spins all want to cant slightly towards the magnetic field because of the Zeeman energy, right? So this causes each sublattice magnetization to cant towards the field. And that produces a magnetic response, a magnetization equal to the sum of these two sublattice MA and B. So this is sort of a trivial effect, right? So it's just Zeeman energy coupling that cants the sublattice magnetization, and the direction of the observed magnetization is strictly determined by H, nothing surprising. If you were to point a field parallel to the easy axis, then nothing happens at first, but if the field keeps increasing, then you get what's called spin flow. The two sublattice magnetizations spontaneously rotate, not spontaneously, they rotate to be perpendicular to the field, because that's how they gain energy, right? And then they slowly cant towards the field as drawn, right? So again, the observed magnetization is equal to the sum of these two vectors, right? And completely determined by the field. Right? So this is basically simple textbook material, but worth reminding you of. So there is an induced transverse magnetization given as the sum of the sublattice magnetizations, but it's always parallel to H. So this is not what I'm talking about. This is a very unfortunate term because the thing that we are looking at